Okay, sorry for the late start. We are going to do a little bit of homework three, homework three, Connect Four. It's called Connect Four, but it's homework three, but that's why I always get it mixed up. And then we're going to review our containers today, which is going to be a little bit overwhelming. I know there's a lot of slides and a lot of code, but really the whole point is we're going to find that these containers basically have most of the same methods. So we don't have to memorize all of these methods, but we do want to begin to get a sense of which ones are similar and which ones are different and in what ways. So we'll mostly focus on that. Everybody's doing pretty good on your lab, vector of random sizes. Today, we're going to have a pretty small lab using the list container, but we have to use our iterators. So that weird iterator thing we'll review today a couple times. We have to use that just to reverse a bunch of numbers. So we've all done a function that reverses numbers, but we're going to have to use something other than the square brackets this time to do that. So that'll just get us kind of using that because we'll need that on our homework 3, which is our Connect 4. Okay, and then a big quiz coming up. And then looking ahead, our quiz 4, remember, is ungraded. Gosh, we're already up to the midterm kind of, it's coming up, and that's halfway, and then we go straight to our spring break after that. So we're really not too far away from that final ungraded quiz in our first half of the semester. And then we'll have our midterm review, and then our midterm will be in class on Thursday night at 5:40 p.m. So we all have to be here, of course, for that. And there will be, of course, no AI for that and all that good stuff. So we'll talk more about that as we get a little closer, but we're really not that far away. Very, very quick review. A reminder, Quizlet is out there. So for example, if you were feeling maybe like you needed some focus practice to understand all of this operator overload stuff, this particular study set here on the second link will kind of just show you quick question, one line of code, quick question, one line of code. And if you can like get all those right, in learning mode, just keep hammering away at it whenever you have a chance. It's going to really help your quiz scores, your midterms, your final exam. It's a lot of it is about recognizing code patterns. So hopefully those things will help you. And I'll remind you from time to time if I have a special one I put together that helps with a particular topic. So last time we did our vector of vectors, and this thing in here is what each row is comprised of. So in this case, I have a vector of rows, and those rows are vectors of integers. So if we just remember that that inside section is describing the row, then we know what we're pushing back every time, even if it's an empty thing. So here we have an empty thing that now becomes the 0th item because there was just nothing in there before. Now the first item and the second item, etc. Okay. When we push back into square bracket something, that's the row we are adding something to. So we just got to get used to recognizing and remembering we're adding a row or we're adding something to a row. And we'll see a lot of that, of course, in our constructor for homework 3. But we kind of saw this last time. And I won't take you through all that stuff again. Now, if we want to erase stuff, I mentioned that, one of the reasons these iterators are so useful is that they allow us to erase relative to the beginning or end. So sometimes if we're doing multiple erases, the index numbers would change. Like what was in the number 2 position might no longer be in the number 2 position. But when we say something like erase relative to the begin, that's a very constant thing that we can always assume is going to be consistent, right? Can erase from the beginning up until the end, or the beginning plus 1, right? So start at the beginning, go plus 1. So that way we don't have to worry about something maybe changing in the middle. And when you start using erase in the middle, then things start getting pretty crazy. So yes.
Could that also, or actually, no.
Okay, all righty. So we'll see more of that stuff today, but there are lots of good reasons for using these iterators when you start doing more intense stuff. Today we'll cover a couple more hints on Connect 4, And then we will go through all of our sequential containers. So that includes vector, of course. We're not going to really talk about string. We're going to use all the other ones, and we're going to compare what it would be like to implement a deck of cards using one of these containers. Now, for homework number 4, you're going to be doing a card game, and you're going to be doing it with a list container. So our final practice today, or almost final practice today, it will be very instructional for your homework 4 once you get there. But these are our containers that are all considered sequential. Today, we will skip the string and just sort of look at vector array. It's like, whoa, there's a container called array. How's that different than just array, right? That was one of the things that confused me when I first recognized these things. And then deck, list, and forward list. So we'll focus primarily on the top 4. I don't think we'll get enough time to go through forward list today, but you'll kind of see the pattern there. So if you want to understand all these things, the best way to do it is just implement a deck of cards using a vector, then change the code to implement it with an array and a deck and a list, etc. So that's what we're going to go through practice by practice. And the code changes are actually pretty small. So they hopefully kind of illustrate the difference between all these different data structures. So for us, of course, we want to think of what's the top of the deck and what's the bottom of the deck in a consistent way. So we're going to think of kind of position 0, typically, but not always, typically position 0 in some array or vector might be the top of the deck. But whenever we deal from the top, we want to do it in a consistent way. So just keep that in mind as we kind of dig into these different data structures and implement typical kind of card operations. Yes?
Array, like a sequential container is different from, like an array sequential container is different from a regular array.
Yes, exactly.
So is that the case for all of these, or is just like array special in that way?
So these are all part of, basically, these are a C++ class that's masquerading as a data type. So even though I color them yellow there, they're not really like int or char. So the square bracket array that we kind of probably knew before we even used vectors, that's a pretty old-fashioned data type. So when we say array here, it'll be more clear when I get to that section, I think, how that's different. But I would say these are all super modern, very safe code, very optimized, and probably the more modern way of doing data structures, except unless you're doing something very, very low level. And I'll explain kind of what that means as we go forward. So let's look at Connect 4 real quick. So our game, of course, if you want to play it, you can kind of find a couple of these on the web. So good to familiarize yourself with how it works. But basically, we're going to have some new private data members, an empty token like before. We're going to also have the players' tokens this time inside of the class. So our class will be able to go look up not only how many players we have in this vector, but what their token is. So this gives us an opportunity to give our players an ID number, and we can just treat them based on their ID in the position in the vector. So player 0 is whatever token is stored in position 0. Player 1 is whatever token is stored in position 1. So if we wanted to grow this into a 4-person game or a 5-person game, we just sort of let the constructor give us more tokens, right? So if you construct your Connect 4 with 5 players, that's okay, right? Your game should be able to walk through each one of these players and just let them take a turn. So you could play Connect 4 with 3 players, right? Or you could play Connect 4 with 5 players. That's possible. It'd be kind of a weird game, but your code should support that. And the main way we do that is using a vector that expands based on what your constructor is given. And then we just need an integer that reminds us which one of these players is the current player. So the current player ID is really just a position in our player token. It's like, hey, what player are we on? We're on player 0. Okay, let's go to the next player. We just add 1 to the current player ID. Okay, so that idea allows us to handle a more flexible description of how many players we have and who they are. Now, the next player method is going to be the thing that is responsible for incrementing and doing the modulo on the next player, right? So we're going to put all of that logic for moving to the next player and wrapping around in one small method there called next player, okay? So, but that is the private data member that we're going to be modifying. So when we want to know what the current player's token is, we just say player token square bracket current player ID. Those are both data members, private data members of our Connect 4 game class. So that's a really easy way, one easy way for your methods in your Connect 4 to actually get access to that information. Okay. So now at the end of the game, when somebody wins, right? Somebody wins the game, we're going to store the winner in the winning ID. So that's not the token, it's the ID, right? It's like player 0-1 or player 1-1. If the winning ID is a -1, that means it's a tie game, or maybe somebody quit the game, right? We don't know who the winner is, okay? But the winning ID should very easily tell us who the particular winner is. So our board is, of course, going to be a vector of characters. So we're switching over to this two-dimensional vector kind of thing. So your constructor is going to have to grow that thing, kind of like we've seen in the recent practice problems. And then as we play the game, it will slowly fill up by having people drop these tokens into a particular slot. So if it's my turn, all I got to do is say what slot I want to have. I don't have to say what I put in each slot. I just say, hey, I want slot number 5. And then the next player goes, and the game knows what their token is because the game knows who the current player is. So each turn, each user input is really just collecting a number for the column, okay? And we're always going to have 6 rows, and we're always going to have 7 columns for our particular game. So those are kind of like constants inside of our game class, okay? So take turn this time will be, of course, updating the board. We called that grid last time. We're going to call it a board now, okay? No good excuse for that. I just kind of changed it. And then inside of our constructor, so these are the constructor arguments. Of course, we could be given an empty token. We could be given a vector of any number of player tokens, and we're just going to use characters again for those. So we're going to just keep that as a reference, okay? And then we have our init tokens. So my unit testing, when I test your game to see whether you are actually doing the right thing for who wins or is it a tie, I will set up your game using those init tokens. So a lot of that same stuff you did in tic-tac-toe, you'll do again here, okay? And then I might say, hey, we're not going to start with player 0 this time. We're going to start with player 1, right? So I will never really try to fool you by giving you a player ID that you don't have up here. But you could put, safety code in your constructor if you wanted to. Yes.
Last time I was setting the modular to alternate between which player it was.
Yeah.
But I couldn't figure out what would you divide something that gets the remainder 0 and then the remainder 1?
So if you do a modulo 2 and it's 0, then you know that you're on player 0 for 2 players. And if it's 1, then you know you're on player 1 for 2 players. So you'd always modulo by the number of players. I don't know if that answers.
1 modulo 2 is.
So any 1 modulo 2, so it goes 0 in remainder 1. Yes. Yeah, exactly. Yeah. So you'll get a 1 remainder when you say 1 modulo 2. Yeah. 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 Goes in 0 times remainder 1. Yeah. So those are our private members. Here's our method. So of course, now we're going to move all of our game logic from main into the actual play method for the class. So all of that while loop stuff is going to be put in there. And I've written it for you, although I've commented it out. So all you got to do is uncomment it in your CPP file. But I wrote it for you so you can kind of see how all the other methods are supposed to work. So you need to write the print instructions, of course, the print board. So it's like your print grid. Get current player token. So this is just a simple getter. It's almost a one-line function, right? Next player, that's just moving your current player ID forward, okay? And then get winning player ID. So these are all pretty basic. I won't say they're easy, but they're certainly easier than the rest of the stuff you have to write. So if I were you, I would just write these things first because they're pretty much getters and setters. The take turn is really where you just need to put something into one of those slots. And we'll go over that here in just a second. And then the is win and the is tie. Those are from, you can probably know from experience with tic-tac-toe, they're going to take you kind of the most time. And for those of you who want to go after something like this, feel free to. There's a take turn, take AI turn method in there as well, but you can ignore that if you don't want to do that. So the top one is done. The other ones here are pretty quick to do, and then these are take a little more time, right? Of course, in addition to your constructor, which you may want to do also pretty quick just to get things up and running, okay? So that's really what you got to do there. So in main, just to show you how much simpler things get, so once we construct our game, right? So we say, test me, create the game, and you could create it in a variety of ways, like with tic-tac-toe, right? So you could specify an empty token and then the players this way, or you could create a variable for the player tokens and pass the variable in, or you could kind of do it all. You could create a current game board that's a vector. That's what I do when I test your program. I just create a game board. There's one long list of these kind of tokens, and then I just pass that to your constructor. So you could do any of these in main to test your code, but then you're going to say game.play, okay? So that's just going to send execution into the play method, and it's not going to come back out until the whole game is done, okay? So that's how you're going to play your game. And all of the looping and the inputs and the outputs are going to happen deep inside of the class, okay? So now our class is fully managing the execution of our game, okay? Now, later on in the semester, we are going to learn about multi-threading. So in that scenario, we'll figure out how we could run multiple games at the same time in one C++ program. That's pretty darn cool. And because we have these totally cool 12-core machines in here, we could do some crazy stuff on lots and lots and lots of threads. So we'll do a little bit of that toward the end of the semester. But that's the nice part about wrapping this stuff inside of a method or some constructor is it gives us the opportunity to start utilizing multi-core or multi-threaded architectures out there, which is really almost everywhere now, except in our cell phones. So fun stuff. So that's our main. And the method, again, the method is kind of laid out for you. So you can look at it. You'll need to uncomment it when you're ready, right? Because otherwise you'll have like a bazillion, compiler errors because you haven't written these methods yet. When you're ready, just uncomment it. You'll see the while loop. You'll notice, and I just chose one particular pattern, right? This could be rewritten in other ways, but I'm just saying while it's not a win and while it's not a tie, and just as a reminder, I threw in the this on our lecture today. It doesn't mean that you have to use it, but as some of us have seen, we kind of forget, hey, I'm inside of the class, right? I'm in a outside of class specification, so I can reference my methods and I can reference my private data members with no problem. Oops, sorry, that's not a private data member, that's a local. So this is just reminding you, yeah, that's one way of getting access to it, but we could just call it print board, right? Or is win, or is tie, or next player. All of those things can happen without the this if you wanted to do it that way, okay? But that play is written for you, so it should give you a sense of how all these other methods should work together. And you should not need to change this. I don't think I have an issue with you changing it, but you cannot change the .h. So that's the only thing, the only real restriction that I have here. Notice here, this is a crucial thing. Usually one of the stumbling points in this game is somebody in their game will have a take turn and they'll have the take turn call the next player, right? And now we've skipped over a player. So don't do that inside of your take turn. Let me do it over here inside of the main loop here, okay? So it's just you know, it's just a convention choice, right? There's no exactly right answer there, but make sure you don't tick forward your next player. Let it happen inside of our play method here, okay? So I'll remind you that a little later as we go forward. But that's all written for you, so you can kind of go after that. Take turn, just a couple reminders. So you're going to prompt the user inside of your take turn method. So that's your responsibility now. So prompt the user, collect a number, make sure it's a valid number from 1 to 7, adjust it down to 0 to 6, right? And then we've got to make sure that column is not full, right? In Connect 4, we can't put an X in column 5 if the column 5 is already full. So your take turn method has an extra responsibility this time. It has to check to see if there's an empty token here or here or here. It has to search for the last empty token and then figure out where to put your new thing, okay? So if that row is full, you can't take that turn and you have to return false, right? So that's an invalid request by the user. We return false. And then the main, of course, will not call next player. It will just go back and ask that player again to take a turn, okay? So you're not looping inside of your take turn, but you are prompting the user for some data. Now, if it turns out that the column is empty or almost empty, you're going to have to search to find the last empty position, and that's going to be where you're going to put that particular player's token, okay? So that's the newer, trickier part of the take turn, okay? But at least you don't have to figure out what row it goes in. Well, you have to figure out what row it goes in, but the user is going to just give you a column, and then you'll have to figure out the row. So you don't have to figure out the column. The user will kind of tell you. And if you do make a move, of course, you'll confirm that you made a valid move by returning true there, okay? So again, please don't advance to the next player inside of this method because you'll end up just kind of skipping over some player at that point, okay? Questions on take turn? Okay. Okay, so just general hints. You might, instead of doing this all the time in your code, you could just, you know, do that eat your own dog food thing they say in the software industry. Call your own get current player token, right? So if you need to know what the current player token is for any particular reason, just call your own method and it should return the current player token. And that way, once you get that thing working, you don't have to worry about making a mistake over here somewhere else in your code, because that will always be fixed, you know, in your method. You also might want to rely on the private data members, num rows and num cols, so you don't get confused about which one's which. So we always have 6 rows. We always have 7 columns. And a lot of times that throws people off. Because in tic-tac-toe, it was a 3x3. So it was perfectly square. So you could have swapped row count for column count. Here we got to get the right numbers. So keep that in mind. Okay. And when in doubt, go back and study your blueprints. Look at your connect4.h to make sure you are picking up on all the hints and comments that I leave for you in there. Okay. So a tie occurs when the game board is full and there is no win, right? So that's one clue you might want to consider. And also a win can occur, and also a win can occur anytime 4 or more of the same token exist consecutively in a row. So they have to be one after another. Okay, so I'll show you some more hints on that in just a second. So it's not like tic-tac-toe where we just count 3 and we can't just count 4. We got to make sure they're next to each other, right? So that is a little different code logic when you're going through your is-win, okay? So anytime we have 4 together, right, in a row, right? So if I want to know how many X's are on a specific row, one way to do it is to set a counter, right? And as we go across that row, if we see an X, we increment the counter, okay? But if we don't see an X, we got to reset that counter to 0 and keep looking. We can't give up on that row just because we find a gap, okay? We have to reset the counter and start counting from 0, right? Okay, now I need to start counting to get 4 in a row again. So if you ever get to 4, then you know it's a win and you can return true right away. So that's the strategy you're going to follow for your rows and your columns and your diagonals. Just keep a counter, reset it when you hit a gap, and as soon as you get to 4, return true. Just get out of there and return true. No reason to keep going, okay? So here's a couple examples. I'm searching. I get a count of 2 there, and then it sets back to 0, right? So I never really get to 4. Here, I get to 4, right? Of course, and that's going to be a win right away, okay? Down here, searching, get a win over there, okay? So you'll figure out how to debug these things. The trickier one, I think, is this one, because if you start looking for 4 over here and you don't have your loops set up correctly, you're going to crash, right? Because we can't really go just down one diagonal or the other diagonal. We got to look down multiple diagonals starting over there, okay? So lots and lots and lots of ways to write that code, okay? So keep that in mind, but generally the same strategy is going to be, yes. Yes, you can write a loop. Yes, you absolutely can. It's a pretty cool little piece of code. It's a little tricky, but yeah, no, it can be done. Yeah, you can do that with a good for loop. Yeah. Yeah, it's a little bit of work, but I would not try to do all of these things in one big loop. I do this one, then I do this one, and then I would do this one, and maybe I would do this one separately, right? So same kind of thing. Okay. So that's your kind of last big challenge on that one. Okay. Yeah. It's going to be a lot harder, if not impossible, to do if this and this and this and this, right? We're going to have to come up with a more algorithmic approach to walking across those rows. Okay. Okay, so just a reminder, and this is a hint, we're obviously not printing columns in this, but if you wanted to print all of the columns in a 2D vector called G, notice that the size of our column, I'm stealing from row 0. Like, how many columns do we have? I guess is probably what I meant. How many columns are there is the size of row 0, assuming we have the same size columns all the way across, right? And that will be the case for homework 3. So if you know how many things are in each column, right? Those are the vertical ones, of course, right? Now we can have our column loop on the outside. So we're going to go across columns, okay, for num columns, and we're going to go down the rows for row equals 0 to the number of rows. And notice that I got my number of rows from the size of the 2D vector, okay? So kind of reaching back to what we talked about, just getting to know these 2D vector things. The size of the grid is the number of rows. And then if I reach in and grab the size of a particular row, that's how many things are in each row. That's the column count, right? So keep that in mind as you contemplate calculating your win. This is just an example of printing a column. So you're going to be doing something a little more involved than that, okay? So I'll leave you with that for now, and we'll have time to come back and talk more next week about it. But any final questions on homework 3 before I press on? Okay, very good. Containers. So these are our containers again. So we know about this one. We've known this one for quite a while. So today we're going to look at this and these here. We probably won't get time to do this one. But for those of you who have taken Comp 220, we will be talking about data structures that you actually built in that class. Singly linked list, doubly linked list, queue or stack. So these are actually professional versions of what we built in Comp 220, which is really nice. We don't have to go build them again. So I'll kind of throw out a few tidbits as we go. In fact, this is a hash table, right? So some of you remember nightmarishly our hash homework assignment from Comp 220. So wow, that's completely shrink wrapped and ready to use off the shelf. So today we'll look at these in the context of cards, and we'll come back over here and look at these later on, probably in the next week or two. Okay. So those are the ones we're going to go through, and then we'll come back to that. So let's look at the idea of a card game. So I like, coding up card games because it just, it seems, hard to really get a card game going. But once you do the basic methods, the fun starts, right? So remember when we play cards, like you have some cards, I have some cards. There's some cards in the middle that we draw from. There's cards that we discard to. So you could call that a hand or a deck or a pile, but that's kind of a class, right? So whatever you want to call that, it's a collection of cards. And we might want to do things like deal from the top, deal from the bottom, right? But we could use that class for a lot of things, right? We could play a number of card games that are pretty complicated, like poker or rummy or Uno, whatever your favorite card game is, as soon as we have some of these operations. So very often we want to peek at the top card or peek at the bottom card or deal a card from the top, right? Typically we're dealing from the top of the deck. And maybe we want to search the deck for certain kinds of types of cards. So these are just really, really useful operations. We might want to be able to sort them, although we won't do that today, but that's definitely something really useful. Or, take one off the top, discard, or give a card to somebody else, like if we're playing Go Fish or turn them over. So once we implement all of these methods, we can now play a whole variety of card games, which is really fun. So looking ahead a little bit to homework 4, we're going to do blackjack, right? So the kind of things we're talking about today, you can come back to this lecture, in a couple of weeks when it's time to do blackjack. You don't have to turn blackjack in until after spring break. So you got lots and lots of time to kind of soak this stuff up. But our lecture today is going to give you all the tools you need for that, okay? So, and I'll remind you this as well, but if you want to know how do you play blackjack, there's some online links you can look at. So this is just down the road, but our lecture today is really kind of all about cards. So we'll let you kind of come back to this if you want and study these, okay? We got lots of time to actually do that. But first we have to have a class for a card, okay? So a card is just going to be a super simple class for us right now. And we're going to give it a value. We're not going to really give it, hearts and spades and stuff like that. We're just going to give it a number for now. And we want our card to have a constructor, right? So if somebody gives us a value for the card, a V value, we're going to stuff it in the value data member here, right? So this is our constructor initializer, okay? And then we're going to put our friend, the stream operator overload in there, so that whenever anybody prints a card instance, it just automatically writes out its value. So this is not really completed here. We got to fill that in with something, but that is really what we want to do inside of that overload, okay? So that's our kind of typical thing. So we can say card C10 and then just C out card C, right? So that should print the C out on the screen according to whatever code we put right in here, right? So that can be, this card is a 10, right? Or a 5 or whatever that value is, okay? So that's the idea with our card constructor. Now, I know we're a little pressed for time, but let's take a look at this one and see if you can kind of, finish this one out. We're not writing the whole overload. We're just finishing it. So take a look real quick and click in and search for the to-do, T-O-D-O. That'll help us a bit today on this one. So some of the things I'll be looking to have you do will include the libraries, but this one, I think we have everything we need. So just print out and notice the value that we're being passed in is N, ampersand N on line 21. So when we say return OS stream, then we're going to say N dot, right? N dot value, right? Because N is a card, okay? It's a card and it's not a card star. So remember our stars versus not stars. Card means that if N is a card, we want to get access to its data member via dot. So we're just going to return OS N dot value, right? And so that should allow you to print that thing out. So now on line 29, just create an instance of the card. So remember, our data type is card, and we need to give it some constructor value, or we should, if we want to control what the value of the card is. So let me kind of show you some code here, kind of keep this moving along. So there's my n dot value. And so here I'm saying card C parenthesis 14, okay? That's creating an instance of the card right there. It's not a pointer to a card. It's an actual card, so that I can just feed that card instance into my stream operator overload, okay? So all of those data types line up. This is a card, this is a card, card comes in here, card dot value. You should be able to see the synchronicity of all that stuff together, okay? So that's the foundation, and now we got to build our deck, right? So how are we going to build a deck of cards? So deck of cards, we got lots of options, right? So the idea with the deck is let's make a class, right? Now, in the old days, before we had containers, we would do something like this. We would say cards 32, and that is going to immediately call the card constructor 52 times, but they're going to be default card values. And notice your card is has a private data member value. It's not got a public data member, and it's not at the moment a friend, okay? So because arrays don't know how big they are, we're going to keep count of how many cards we currently have in the deck, okay? So I know we're always going to have 52 cards spaces, but if we discard from an array, what do we do, right? We can't really delete any elements in the array, so we need to keep count of how many cards are actually in the array, okay? So this is going to be the basic methods of our class that we're going to build out here, okay? So the first thing we need to do is just sort of the straightforward stuff. Print me, right? So the top card would probably be position 0, or should we print it out from the bottom? So if we're going to delete cards, we're probably going to have an easier time deleting them from the rear end of the array, right? Sort of basically just counting backwards and skipping some cards that we pretend are deleted, okay? So we kind of have to imagine with this old array that we can actually delete things, but we're not really deleting them. We're just sort of ignoring them, okay? So let's kind of go through this one together. I'm going to give you the code here because I know this is going to wear everybody down. But consider that the first position of the array is at the top of the deck, okay? So we want to put card 0 at position 0, card 1, etc. So 51 is on the bottom. And then we're going to print these things out, okay? So we're going to start by printing from the top down. Okay, so I know I'm probably confusing you here, so let me give you a little help on this. So here's our deck. Here's our count. Our constructor is going to set the count. And notice how we initialize our array. So we say cards of I equals card type, the card constructor of I. Okay, so I'm saying, hey, create a brand new card, give it an I value for its constructor, and then copy that whole thing over the top of cards of I. Even though cards of I already existed, we're just going to write the new card over the top of that in our constructor, okay? Now, some of you might be thinking, why would we do that, right? We'll come back to that in just a second, okay? But keep in mind that value in our card is private, okay? So this is we can do, okay? Now, if we want to print out the deck of cards, we're just going to loop, and we're going to say, go from I equals 52 minus count. So I think I lied to you here. I think we are printing from the bottom of the deck in this one. And continue while I is, wait, for I equals 52 minus count. Oh, that's right. Okay. So if we have 52 cards, and we say 52 minus count, we start from position 0. So I was right. We're counting from position 0. But if I delete the top card, right, now I have 51 cards. So 52 minus 51 is 1, right? So that would start us in position 1. So this is our tricky way of ignoring the cards that we have already dealt off the top of the deck, okay? Really messy. It's kind of confusing. It's really annoying because our array is not trivially, editable. We can't remove a slot from our array, okay? So this is how we get around that problem, okay? And I promise this will go away shortly, right? Once we move to a more modern data structure here. But now we have our print me, we have our constructor, and we have to actually copy the whole card over because we're not allowed to do this right here, okay? We're not allowed to say cards of I, value, gets I. We can't do that because that's a private data member right there, okay? So we copy the whole thing, brand new one, over the top of an existing one. And C++ will let us do that because we're not reaching inside and trying to access an individual private data member, okay? So this is kind of our, our first pass at getting this part of it up and running, okay? So let's take a look at the second part, right? So now we're going to kind of go back and look at some of those methods. So we're going to kind of fly over the top of this one too, to give you sort of a base on this, but you can certainly come back and look at these if you want. So now we want to implement the size method, right? So it's like a getter. How big is our deck of cards? If I've been dealing cards, right, it's not going to be 52. Even though I've got an array of 52, I have to kind of manage simulating that I've gotten rid of some cards. So our size is going to change. If I want to peek at the top card, I have to figure out which one is the top card based on how many things I've already dealt with this old school array, right? And then I'm going to just return that, okay? So I'm returning a copy of the card. That's why we call it a peek, right? Same for the bottom, okay? Dealing a card is going to be returning a copy and decrementing the counter inside of our cards, okay? We have to decrement the count, and everything has to keep track of that, annoying array position that won't go away, right? We have to skip over the beginning of the array so that as we deal more and more cards, we're ignoring the cards at the beginning, okay? So obviously array is not a really fun thing to do. So we're going to just kind of jump into it so you can take a look at it. But try to kind of digest the code here. If you want to try to knock this stuff out real quick, it's pretty easy, right? So return the count is our size method, okay? So that's just how many cards we have in the deck. The top card is going to be cards, square bracket, 52 minus count, okay? So if I have 51 cards, I'm going to start at position 1 rather than position 0, okay? If I have dealt all 52 cards, then let's see, what if I have dealt 51 cards, if I have dealt 52 cards, my count will be 0, right? So I will crash the program. So I probably have to put some safety stuff inside of there. But that's the basic strategy here, okay? And dealing a card is decrement the card count, right? And return the card that's at that particular location, right? I'm giving you a card. Yes, Michelle. Cards of 0 in this case would be the first card if we never dealt any cards. So with an array, when we deal a card, we use the counter to essentially treat those cards as tombstones, right? Where we don't actually go there anymore.
If you had 52 cards, though, and you had a card with 0, so is that what you were saying was like a problem?
Yeah, if you had 0 cards left, right? If you dealt all the cards and that was a 0, and I said, hey, go to position 52, we would of course crash, right? So we probably need a little safety check in there to make sure that I don't try to look at the top card or the bottom card if I'm all out of cards, right? So I don't want to crash my program. But this is obviously really messy, right? And people do write this code. They have to somehow deal with these arrays that are not very changeable. So we sort of take it for granted which we'll do now, and switch to a container, because now the container is managing this messy thing for us, right? But otherwise, we got to come up with some way to actually do all this. So for those of you who took Comp 220, you might remember like vaguely, it's like, oh yeah, I remember like we had to do that thing where we were like doubling the size of the array and copying data around. It's like at a low level, somebody's got to write that code, right? So here we're looking at it, it's like, yeah, this is no fun. I don't really like this. So, but once we kind of get those methods done, main is okay, right? We're just saying, hey, peek at the card, peek at the bottom card. And guess what? Because we overloaded the stream operator for the card class, the deck top card peek prints directly. What do we get back from the top card peek? An instance of a card. But cout knows how to print an instance of the card. So now our code in main is just so much more beautiful. It's like, oh gosh, that's just so much more fun to work with. Okay. So I now have the ability to look at things, I can deal things, right? So the more methods we implement, the easier it gets to write all these different programs. And when I say print me, we're printing the deck, right? We're not printing a card, we're printing the entire deck because D is a deck class, okay? So keep that in mind as you go through these things, okay? So let's take a look at just a high level view. I'm not going to go through all of the extra details on this, but so here are our sequential containers. And essentially, this is a doubly linked list for people who remember this. Singly linked list, of course, right? Double-ended queues. So some of you remember implementing queues in Comp 220. If you take Comp 220, you will. And then a dynamically sizable array, which we won't dig too deep in. It's quite an elaborate implementation, actually. But those, of course, are our sequential containers. And so we could implement our deck of cards with all of these different things. And each one of these different data structures makes one part of the card game a little easier to code up. And I'll cut to the end. This is probably the most awesome container there is. It's also the slowest and most, maybe, least optimal in memory, but it's got like all the features thrown in, right? So some of these things are really stripped down like a sports car, like forward list is super, super light and fast. List has got some other advantages. Vector is kind of the thing that most people use, but the deck, surprisingly, is probably, I would say, the most useful, okay? So we're going to try to work our way through a couple of these things and see how much we can get through, okay? Now, the nice thing is all of these methods, all of these containers rather, share some, but not all of these methods. So you guys might recognize a few of these. Like you certainly know about the pushback and the vector and the string, but maybe we didn't know there was something called a push front because the vector doesn't support the push front, right? And we know about the at and the square brackets, and we've sort of learned about the begin and the end for iterators, right? We just sort of introduced that last time, but I might not have known that I can get a copy of the front of a container or the copy of the back of the container. So that size -1 thing that we've had to do for so long kind of starts to go away because it's like, hey, give me what's at the back, give me what's at the front, okay? So there are a lot of things. So if you learn what all of these things do and which containers support them, you are like a master of that domain, right? So I'm not going to try to teach you all of that today, but we're going to show you that as we go through these containers, some of these things stay and some of them go. But this is kind of the core of the methods that we have at our disposal. And some of them are pretty darn cool, like swapping between two things inside of something or resizing a vector or resizing a container. Those are really nice features to have. Okay. So I won't actually, I'm going to skip over the top of that. So I'm going to jump right to the next section here and dig right into our practice problems. But you can come and read about all those methods, or of course you can go online and read what all those things mean. But sometimes it's easier to just write the code and learn. So let's look at this weird animal called an array. It's like, it's a container. It's not the array that we kind of grew up with, maybe. These arrays know their size. They don't know much else, but they know their size. And they're not pointers. The name of the array is not like a pointer to some location in memory. It's actually an instance of a class called array with a whole bunch of methods. It's more efficient than a vector because it doesn't need to be dynamically allocated and it's not allowed to change its size. So where we would do something like this in the old days, now we do it this way with templates. So that is a really interesting template, array less than int, comma, 6. So our template has two parameters to it. One is the integer type. One of them is actually a number. And that's okay because the template manager, remember, it's kind of like copy pasting that stuff all over the place. So it's just taking the 6 and going, oh, I'll just use that 6 as one of the pieces of information for your array. Okay. So now we have a 6-sized array that knows how big it is and supports iterators and a few other very nice things. And it's more efficient than a vector, right? It doesn't take up as much space in memory as a vector because it's a fixed size. So these are all the methods or most of the common methods that it supports, which is pretty nice. Square brackets, at, front, back, size. Notice there's no pushback, right? We can't add anything to this container array, okay? So here's our creation of that. So you kind of imagine this is what we're doing. And notice I gave it a size of 8, but I only gave it 7 things. So whenever we do that with these containers, of course, we leave kind of something uninitialized. So, and we get the bonus of our begin and end iterators. So all of the kind of things that we can do with every other container, we can do this way. So we can go through it without changing our code. So if we adopt an iterator code pattern, then it doesn't matter what container we're using if we want to go through all of our different items. Yes.
Didn't they created a string that the type of character has the exact size of 0? And
Yes.
that like was included in the size.
Right. Yes.
Things also like included in the size.
No. Correct. Yeah. That's a great question. Yeah. The empty bumper there is not included in our size. So the array class and all the container classes sort of do the right thing. It's like, I'm going to tell you how many things you have in here right now. Yeah. So that's a great question. So that's our array, right? And so if I iterate through that, I can say, give me what's at Q, kind of like a pointer. So we'll see that again. And we'll kind of dwell on that here because I know we covered it last time. But this is how we create an array, okay? And so, it's always going to be size 8, no matter how we initialize that thing. So we got to be careful to give it the right number of initializations in there, okay? And the rest of this stuff is just standard protocol for containers, okay? Now, we don't want to get too happy about getting a nice 0 because containers often initialize things with zeros for us. But in the rest of the C++ world, we don't often get that nice initialization. So be careful not to count on it too much. So here's a view of all of those methods again, but just the ones in green are the ones that the array supports. So I don't expect you to memorize this. It's just hard to find this information in a digestible form. So you can kind of see the grayed out ones are the ones that we don't have with the arrays that other containers do have. So it's a pretty stripped down set, okay? So again, I think I will just, because I can feel the pace, I don't mean to rob you of the opportunity to write this code, but I want to kind of get us to the list container at the end because you need that for your lab. So, so bear with me while I go through this. But let's say we wanted to strip out that old array from our previous solution and swap in this new container array. So it's still a fixed size array. So we still got to do that counting thing, right? Still got to do a little bit of that messy stuff when we deal a card. But basically, there's not much else that's going to change. So let me just show you what the changes would be, and you're welcome to jump in and do them. But here I'll highlight them in a dark blue color here in a second, right? So all we're really doing there is swapping out what was the old array with this new container array and telling it that our data type, of course, is going to be card, and there's going to be 52 of them, right? So now we have 52 things in a more modern container, and the rest of our code just works, right? Because We don't have to change it. The square brackets work. It's no longer an array. It's a C++ class masquerading as an array because it's overloaded the square bracket operators, okay? So that's the real nice benefit of having overloaded operators, is because we don't have to go change all the rest of that code we had. Yes. This template parameter right here tells it, it's kind of like vector int. Yeah, exactly. Yeah. So card is the data type and 52 is how many of them go in that array. Yeah. So glad you asked that question. Yeah, because we look at it, we're like, wait, where's the data type? Well, it's part of the template, right? Yeah. That's why that template, understanding those templates is so helpful, right? So that was the only thing we needed to do. So now let's go to something we're a little more familiar with. So a single-ended queue or stack, that's really what a vector is for you Comp 220 folks. And they grow dynamically. So we don't have to worry about dynamic allocations and deletions. When we push back, the vector class is doing a whole lot of pointer stuff underneath, but we don't have to worry about it. So that's really nice. So if we include that vector library, we get all of these good things. We can see what's at the front and what's at the back, and we can swap, right? We can see if it's empty, but we don't have any of the cool push front stuff. We just have the push back, okay? So it's like, I wish I could have had some push front, push back, but a vector is really a stack. So we know, if we know what stacks are, that we're only going to get to pile stuff onto one end. So the back end of the vector is really the top of the stack, again, for you kind of algorithms folks, okay? So a couple other cool things, but that's really primarily what we do. And we know how to make them, and the code for looping through them is identical to our array. It's a common approach. We don't have to, of course, we can use square brackets, but we could use this iterator kind of thing that we're going to use in our lab today. Okay, so we'll dig in on that a little bit later. Okay, so a few more methods, right? So we get some back end methods, but we're still missing the front end methods because it's just a stack after all. Okay, so we won't dig into all of those, but you can kind of get a sense of that. And there's something, by the way, for those of you really looking for advanced stuff to do in your spare time. You can read about and place. So that is probably one of the most powerful methods. We don't really cover it in this class, but it's a super efficient way to put things inside of a vector. So I'll just leave that with you folks who are looking for something a little more advanced. But let's quick fly over the top of our vector again and see what we got to do. We're going to change our data structure. We're going to change the cards in the deck class to a vector type, okay? And we're going to start to use a pushback whenever our constructor wants to add a card, right? Because like homework 3, we can't assume our vector is going to come with 52 things. We're going to have to push them back. But now we can use our dot size from our vector, and the print me actually can use the dot size, and we can use cards dot front. So cards is now a vector. So I can just say, hey, what's the front card? Give me a copy of that thing when I peek at the top card, okay? So if the beginning of my vector is the top of my deck of cards, I can just grab from cards.front, and that gets me a copy of the top card on the deck, okay? Same for cards.back if I want to peek at the bottom. And deal a card, we use our little eraser trick. We say cards.erase the beginning card. Okay, so that was our erase review slide from a little earlier. And I know it's really hard to keep front separated from begin. Begin is the card, front is the card, begin is the iterator. See, even I trip over that, okay? But this is our very nice way now of dealing a card. It's like, hey, I'll take a copy of it, and then I'll erase it, and off we go, okay? So we'd take a copy of it with front and then get rid of it and then return that to whoever asked for a card. So if we're playing Go Fish, it's like, hey, let me make a copy before I delete my top card. Here's the copy, right? That's exactly what we do in that case, okay? So let's look at the primary code changes. So we get all the code up on the screen. So that changes, right? We changed from our array to a vector, okay? And now we have this much cleaner way of dealing with the front. We don't have to deal with that whole nasty counting thing anymore. And the back, right? And then here's our deal a card. Let's just spend a moment looking at this. So if we've got cards left to give, then we'll do this. Otherwise, we got to return some kind of card. So typically the way we handle this problem is we create some definition of a fake card or a bad card or a joker card, and we flag some error, or we might raise an exception so it can be handled separately. So there's lots of ways to deal with that. I sort of took the easy way out here. But notice what we're doing. We're getting a copy of the front card and holding on to it, erasing the front card or the beginning card, and then returning that copy, okay? So that's me giving you a card. It's really a copy of what I just erased, but as far as the card game goes, we can treat that as the same thing, okay? So that's our vector, okay? So I think everybody's pretty familiar with that. Let me just keep plowing ahead here. So there's our deck. I used to call this DQ, but apparently that is not how you're supposed to pronounce it. It's a double-ended Q. So we have the head and the tail, or front and back. So now we have access to the front, just like we do with the back inside of our vector. So we just sort of create deck int, just like a vector. So all of that stuff's pretty much the same. We get front and back like before, but now we got push front, pop front, right? So we can add and remove stuff from the front and the back. I think I forgot to mention pop front on the pop back on the vector. That's really handy. So I can push and pop stuff off of either side, which gives us lots and lots and lots of flexibility. Okay. So now we can actually kind of have an easier way of erasing the top card when we deal it, right? So here's our creation of our deck, right? And our same iteration code works for everything, which is very nice, okay? So that's all of our pointer stuff. And here are our methods again. So we kind of lost some things, but we gained some things. So I won't drill too much into this, but most of the stuff is there, right? That's pretty cool. So this is a very, very powerful container. And jumping into the code, if we want to upgrade our vector, of course, we're going to change our constructor. So we're using this different class here. Okay. So there's our deck. Our deal a card is really the only thing that really changes. We just say top card gets cards front, and then we say pop front. That's our new method that we got. So we no longer have to do that somewhat tricky erase, right? We have an actual method allocated to it. Okay. So now you may ask, well, you know, why don't we just use vector and use the erase? Why would we ever want to use the DQ? Well, the deck is really fundamentally a different data structure underneath. So it is more efficient for deleting or popping front than the erase. Even though we can erase the front thing from the vector, it's not a very efficient thing. It's causing a lot of deallocation underneath the surface. So the deck is going to give us a more optimal way of deleting things from both ends of that particular data structure. So that's kind of one of its benefits, okay? And that leads us to our last one, which will get us ready for our lab. So when you start homework 4 and you're looking for some direct, mainline help, you can kind of come to this area. But a list is just a doubly linked list. And if you haven't done one, we'll definitely do one in Comp 220. but it's not an array in any way. There's no memory allocation of some big collection of memory space. It's a bunch of little nodes hooked together by linked pointers, okay? So it's really made for inserting things in the middle, splitting things up, you know, sorting lists, that kind of very much pointer types of stuff. But it comes wrapped in a very nice software package for us. So we can create a linked list like this, right, with all of these members in it. And we can do all the good common stuff, swapping, getting what's at the front and the back. We can push front, push back. We now have more direct insert or more optimal inserts and push fronts and push pops, but we no longer have our square brackets. Okay, so now we are forced to use our iterators. And so that's, of course, what homework 4 is going to be all about. Okay, so we have to actually, we cannot use, hey, keep going while I'm less than the END. We have to say, well, I'm not equal to the END, right? So that's why I've kind of pushed that as the most common way to go through your containers, is by testing if we're not equal to the end, right? So that's probably the safest way to do that, okay? So don't forget, I know some folks will wonder, why aren't those square brackets working in my code, right? So that's just one of those things we won't have in our list container, okay? So here's how we create it, right? Of course, here's the list code, the iterator code again. It's the same for everybody, which is just so nice. Once you memorize it, you got it, and life is good. So that's our list and list iteration. Here's our methods, right? Okay, so just a nice place to come back to if you have to figure out what's supported or not, okay? And let's take a look at our code. So if we want to upgrade, this is our final upgrade. We won't really do our final forward list thing here in class. But if we want to upgrade this one, we do have to change a few for loops, okay? And we'll have to do that inside of our print me, right? Because our print me has to go over all of the items in order to print them out, okay? So, and then of course, upgrade our data structure. So here's our kind of final thing. There's our deck of cards. Just coincidentally called a deck, but it kind of is like a deck, right? Our print me method is the primary method that's going to change. And so here's our iterator for auto iter. You could call that Q or I or whatever you want to call it, but think of it as a pointer, right? So for iterator starts at the beginning card. That's an iterator, not a copy of the card. And continue while it's not equal to our bumper and increment the iterator, okay? And then we can dereference the iterator. And what does that give me? Any guesses? If I dereference the iterator on this? Instance of a... Yes, what's it pointing to? An instance of a... Yes. Thank you. I knew you do. I knew you do. So yes. And in fact, even though it is acting like a pointer, which is exactly what it's trying to do, again, the iterator class just overloads the star to make it seem like a pointer. And underneath, it's doing all the work to figure out where it's supposed to go get that number. So we don't have to worry about how the deck does it. It's like, hey, star iter is always going to give me the thing that that iterator is pointing to, okay? So, and I'll say pointing to in quotes because it's not really a pointer, but we often just say, call it like a pointer, okay? So that's the moral of that story, right? Everything else just kind of works. Now, that's a double linked list. We can go forward and backward. We can delete stuff off the front, delete stuff off the back. If you downgrade to a singly linked list, again, comp 220 folks, we no longer can easily travel to both ends of the linked list. We can easily get to one end of it, but not to the other. And so we tend to lose any operations at the end of the list when we work with a forward list. So I'll just show you that real quick. Like, look at all this back end stuff we lose. It's like, whoops, sorry. You can only do things at the head of the linked list, so there's no more back end operations, okay? Now you can do things using erase after, right? but it's going to cost you. The performance is going to be lower because it's got to follow all those links to find whatever it is that you want to erase something after, okay? So, and we cannot go backwards. We can't walk backwards up that chain. So everything else is really pretty much the same as the list, right? The iterators are the same, right? We want to go forward through the list. We just can't go backwards through this list, okay? So that's, that's it. And so there's, we lost a lot of stuff, but we get to go really, really, really fast, right? And we get to have lots of, efficient storage and memory of our data, okay? So that is something also we lose is the brackets, right? Because we have a linked list here, so no more square brackets. So I won't go over this one again because I want to summarize the lab and sort of get you guys out of here. But if you want to come back and try this one, you can. The only thing I'll say is high level, really high level, quiz 3. Yeah, quiz 3 will just sort of ask you like, hey, what's the difference between these things? Or what are the primary things you can't do with a forward list, right? Can't put stuff at the end. So that's really the key takeaways. I don't expect anybody to memorize these methods, but it is good if you know how to find the answers efficiently online. So you might want to either study your slides or get your favorite kind of linked pages that you can refer to. So this is all of our practice problems for today. If you need to come back and jump into them at some point, okay? So let me summarize our lab for today, and then we can kind of let you guys do what you want to do. So this is just a simple get reverse function. So I'm going to give you a copy of a list, right? A list container, right? So if it's 1, 2, 3, you're supposed to return 3, 2, 1, right? So typical kind of reversal kind of thing we do in intro C++. So, but the data type is list int. So we get handed a list int, we get back a list int. So you're going to need to create some way of storing something as you're reversing it, and then return that thing as a list, okay? And I don't think C++ will let you use a vector and return it as a list. So you probably have to work with a list inside of your reverse function, okay, in order to actually build that thing up as you go. So, and remember, you'll have to use your iterators to do that. And if you want a little bit of a challenge, this is just optional and for fun, try to do the same thing with a vector. Try to force the vector to go backwards. That's another interesting exercise. But this is our primary one, gets you ready for homework 4 a little bit, okay? And main is already written as usual. And that's it. That's all we got. So sorry to rush you through that, but I think that would have probably added a 15, 20 minutes onto our lecture part. So any final questions before we kind of adjourn into lab? Okay. All right. Thanks, everybody. I'll see you next week on Tuesday. And don't forget your homeworks if you're still working on them. Okay. Thanks, everybody. Drop them out.